Hi, and welcome to our next science chat, which is also a STEM chat, science, technology, engineering, and math. And today we're going to talk math. And we have with us today Professor Jim Anderson, who is in the UK. Welcome, Professor
Thanks
Anderson.
for having me.
Thanks for coming. May I call you Jim?
Please do.
All right. Thank you, Jim, for coming. So I will give an introduction of Jim's biography. You grew up in the United States and you moved to Southampton, UK in the mid-1990s. Your main interest is in low dimensional geometry and topology, focusing on the questions about surfaces and different aspects of non-Euclidean geometry. When not at the blackboard, you practice the traditional Japanese martial art of Aikido, and you try your hand at writing short stories. Fantastic. So welcome, Jim.
Thank you.
So let's talk about, first of all, where did you grow up in the US? Because as being an American who's engaged to a Brit, I'm curious about this.
I grew up in Georgia, in a town called Athens, university town. We'd actually lived in the Northeast for the first 7 years of my life, moved down to Athens. That's where I consider myself having grown up. And then I've spent time in New York, back in New York, in Texas, and in Northern California before coming over to England.
Yeah, you sound like me. I've been around different corners of the US and now it's to England. So similar path in that regard. I grew up in Tennessee, neighbor state of Georgia. So tell me about what you would consider a typical day in the life as a professor in math.
Okay. Well, I think that one thing that I think a lot of university academics will recognize is that a day in the life depends very much on the time of year that we're talking about. So if we're talking during the teaching semester, then what it will involve is perhaps some meetings, depending on the level of administrative things you get involved in. It'll involve meetings with students. It will involve preparing lectures and giving lectures, and then finding some time to think about the questions we like to think about. Outside of the teaching term, we might be doing a bunch of marking and all the associated administrative ephemera that comes with marking. At times like this, when we're sort of out of our standard teaching cycle, the focus flips more to research, because particularly at a university like Southampton, we have a balance between the teaching we do and the research we do, and there's an expectation that we have things always on the boil. And so actually at the moment I have a visitor in town and we're picking up a project that we've been thinking about for a number of years. I won't go into too much technical detail at the moment, but it's again one of these geometry of surface questions, but it's sort of lain fallow for a couple of years. And so we're picking it up and going back to things we wrote a couple of years ago and thinking, ooh, that was actually quite nifty. We should do something with that. And so that's what we're doing at the moment. And I do actually, yes, have a chalkboard in my office. I'm not in my office at the moment.
Awesome.
But I have a chalkboard, I have whiteboards, we have all the things we need to do math.
Very cool. So, for anyone who's considering doing this as for a living, you have your own path, but I'm curious what you would recommend for someone who might be interested in it. What would you start with? Let's say from high school or the equivalent of that onward. What would you recommend for that stage onward?
So I think there are two different paths, if I may break it up that way. One is the path of being a university professor, a university academic. So this is something which universities will have departments in sort of all fields. And so this is very much it depends on what area you want to be in, but it would almost always involve going through getting an undergraduate degree at a university, not necessarily in the field you're interested in going into, then going on to get usually a PhD in graduate school. There might be then some postdocs. There's a lot of applications, a lot of writing to people and saying, I'd love to work at your university and here's why you should hire me.
Yeah.
And then you try and land a settled position. So what we call a permanent position in the US, that would be tenure track.
Yeah.
And then you go through that process. And then that takes quite a while. And it's not an easy road, but I've found it to be an incredibly fulfilling career choice. but there's also the path of being a mathematician, which I think is a different path, because you can then go, I mean, one of the things that I like about math, in particular pure math, is we keep getting these stories of people who are creative amateurs who come across and do great things. So we can go back to the classic days of folk like Fermat, who was one of the great mathematicians of his day in the mid 1600s, down to just a few years ago. There's someone who's a biologist, actually, named, I believe, de, who actually came up with a solution to a math question that's been open for decades.
Oh, I love that.
Something that he was just thinking about, something that intrigued him, something that he got interested in, something that he spent some time on, and something that he was able to make some progress on. Now, the per hourly rate for such a thing will be low, because typically you need to have the day job to pay the bills. And this is just something where you're getting fame among a very small group of people, typically. But I think that it's possible to be a very engaged amateur mathematician. It's also possible to do mathematical things as a career outside of universities. So I don't know if this is still true, but at one point, the largest single employer of mathematicians in the world was the National Security Agency, for instance. So the mathematics of codes and breaking codes is something that the NSA takes very seriously. They hire really quite a lot of mathematicians. There are jobs in places like finance where mathematical techniques and mathematical tools have become a lot more used in the last few decades. And so there's a lot of, and there are a lot of people who, for instance, will go through and do a PhD and then go off and work in industry somewhere, in some industry. And there are even things that you can do out of an undergraduate degree in math. My familiarity is much more with what happens over here, but a lot of people can go into things like accounting or actuarial work, or, I mean, for instance, even teaching, and then teaching high school or pre-high school. So there are lots of things that you could do if you're interested in math, where you could have a career where you can keep being engaged in math in some way, depending on how much you like it when you get through with your degree.
Great. And from my perspective, having worked in biological research, both in ecology as well as clinical research, I know that statisticians are tremendously important to science. You want to have how significant is the result that you're getting, you need to tease all that out, and having statisticians on staff for research teams is absolutely essential. So that's another career path.
Absolutely. Well, I have to admit, I view statistics as part of the wider universe of math.
Absolutely.
So
just one facet.
Yeah.
So what made you decide in your life, I know it's going to be math for your career track?
So for me, it's basically because I had some really good teachers starting at the end of high school, actually one in middle school that I remember, some in high school, and then getting into university. I just had some really good teachers who made the things really interesting. I had no idea what I wanted to do, and I was good at math, and so I was taking math classes, and these folk were showing me just how interesting it could really be, and I just kept doing it. Now I have a huge advantage, I think, just in the sense that having grown up in the house of a university professor, my dad was a professor. I knew what universities were like. I mean, he wasn't a mathematician, but I knew what university life was like, and I'd sort of seen it from the inside. Good. And so it always struck me as a very reasonable thing to do, because it's just what my dad did. And so I had a good handle on sort of what the problems would be, where the stress points would be. I mean, my mom went back and got her PhD actually in statistics when we were all old enough in school, my sisters and I. And so I'd seen a lot of that, and it just looked nifty. And so I just kept going, and was lucky to keep getting jobs at every stage that allowed me to just keep going.
That's great. So did you go directly into university and onto graduate school, or did you have a break in there in which you worked somewhere else or anything like that?
This is basically what I've done.
All right.
when I was an undergraduate, my parents gave me a choice of getting a job over the summer or going to summer school. And I just went to summer school and accumulated more credits because that was an option. I did have a few small sort of part-time jobs during that time. But I never, for instance, worked in the retail food industry, as I know a lot of people have. I was able to, and then once you get to graduate school, I had a stipend. So I was getting a salary for being a graduate student. And so I just kept going.
Were you like a teaching assistant, a research assistant?
Mm-hmm.
At the grad school? Okay.
Teaching assistant, yeah. It was particularly within math departments. And again, this is something which varies a lot by field. The fact that basically everyone has to pass calculus to graduate an American university means that math departments are huge and have a lot of grad students to teach a lot of calculus sections. And
right.
So that was just part of the backdrop.
Yeah, and I just definitely benefited from a teaching assistant in calculus, from my biology background. I was very grateful for that because I do think that is the perfect liaison between professor and student, is having that teaching assistant, or research assistant, TA, RA, and it just is tremendously helpful for that. And I'm glad that you were able to have a stipend for that. So that's great.
So I think a lot of the science and engineering fields still have that sort of a structure to it.
Yeah.
I think it's becoming less common in non-STEM fields, but I don't know the details of what's going on in the States.
Yeah, and I've not kept up with anything outside of STEM in terms of second, like advanced degree situations. So, all right, well, so you figured all of this out. You did the track. It took a long time. How long exactly did it take from, let's say graduating college, university, and then getting where you are now? How many years was that?
So 4 years at university, and then the PhD program I went into, I finished in 5 years, and that was sort of the average. The average was between 5 and 6. So I finished in 5. Then I had a 1-year postdoc out in California, in Berkeley, not at Berkeley, but in Berkeley. And then I had a 3-year, what they called an instructorship at Rice University in Houston, in Texas, which was, again, there was an expectation of doing research. There was teaching involved, but it wasn't that heavy a teaching load. And then I got the job at Southampton. And so 5 years of graduate school, 4 years of postdocs, and then into the job that I basically still have now. And I think that's on the low end of typical. Again, depends a lot by field. For math, having 1 or 2 postdocs is very standard. I think in other fields, it might be that there's an expectation of a bit more training before getting a permanent job, but that sort of a path isn't all that unusual in math, I think.
Yeah. What would you advise someone who's thinking about a career in math to do at, let's say you're a teenager, like my sons are teens, and they're good at math, they're interested in math. If they wanted to pursue a career in math, what should they do, while they're still at this stage before they even graduate?
The short answer, I think, would be to actually do some exploration and decide if that's actually really the case. So one of the things that we have now is a lot of sort of popularization of math that's, books and articles and things on YouTube where you could explore some of the more interesting topics, or more interesting topics than you might get, say, in a traditional high school where you're going through a very structured syllabus of things. Because one of the things that again, a very personal view of mine is that sort of before university, math is very much here are things that we've known how to do for a long time, and this is how you do them. And we have worked out all of the details and made it very slick. One of the things we start to show at a university is actually there are things we don't know. There are things, different directions we can take things. It's much less here's the way you solve the problem, towards here's a question, what are the things we know that we can throw against this question, and what can we try and find out? So the math we start to do at undergraduate and that we then continue on doing in graduate schools is different from the sorts of things we're doing in high school, just in the approach we're taking to it. It's much less a, here's a formula, how do I use it, to, well, where does that formula come from? So one of my favorite examples, which comes up in our case, first year calculus, is we teach the formula that the area inside a circle of radius r is pi r squared. The area inside a sphere in 3 dimensions of radius r is 4/3 pi r cubed. Where do these formulas come from? Why is that the formula as opposed to some other thing? What's the formula for a volume of a sphere of radius r in n-dimensional space? And so what do we mean by n-dimensional space? What do we mean by a sphere? And what do we mean by volume? And how then do we figure that out? And those are the sorts of things we're starting to work through in a university math curriculum, much more so than beforehand. And so I like to think of it as we're starting to a bit show the wizard behind the curtain of, this is where the things come from that we've told you your whole life are true and that you've been using to do various sorts of things. But we can actually tell you why. It's just that the why takes a lot more work than just knowing the formula.
You know, that's one thing that I do like, that my children's generation, Gen Z versus Gen X were like, here's this, you memorize it, this is how you do it. Don't ask too many questions, you just need to do it. Why? Okay. But for my kids, they have at least learned how to think about doing it. Whereas we just were memorization. Now you think it through. And I really think that's huge benefit to them, because it's literally taking problems and solving them from a creative point of view. And what would you say regarding creative space? You know, like, do you think it helps to have creative outlets in math? Things that you do outside of, no pun intended, the sphere?
I think it's incredibly helpful myself. I think that having things outside of math, one, it just gives me a bit of a break. I mean, I love math, but it's hard to do something 24/7, 365, and maintain the joy of it, I find. But I also just, I don't know a good way of framing it. I like to just take my brain and stir it up every once in a while by doing different sorts of things. So I do a lot of reading. I do a lot of nonfiction reading, a lot of fiction reading. I do the throwy thing that's there on the wall behind me. So that's actually one of my most recent certificate of grading.
Oh, wow.
And also a drawing that's made from a photo of me. I'm the one that's upside down in the drawing, by a local artist named Chris Small, who's someone that I know who does some really nice drawings out of sports photographs.
Oh, that's really cool.
One of the nice things about having something like Aikido, or really reading or even writing when I can convince myself to sit down and do that, is that I put myself in a place where I'm focused on a very different sort of thing with a very different focus to it.
Yes.
And that I find really helpful. So I think having that, at least a significant interest outside of the day job, can only be a good thing.
I agree. I'm very biased in that, because I have a lot of fingers and a lot of pies, not necessarily pie, but anyway, you know, I know I'm going to throw the puns in. I can't help it.
If only we were recording this on the 14th of March.
Oh, you know, it'd be fun to do something for that, like a big Zoom meeting to celebrate, because I like to bake pies on Pi Day, of course. And sometimes I put the symbol on. Anyway, yes, we're nerds here, and it's cool to be nerds. So getting back to the creativity, I'm going to dig into that a little bit more before we move on to some other subjects. So I commonly hear that being good at music helps you with math. What's your opinion on that?
I think that there are some really strong similarities between math and music. I know a lot of mathematicians who are very musically talented. I myself am not one of those. But interestingly, I know fewer musicians who are mathematically talented. I'm sure they are out there, but they both have they both have elements of structure to them that I think are similar. And actually, one of the things that's on my shelf of books to reread, having read them many years ago, is Douglas Hofstadter's Gödel, Escher, Bach, where he actually gets into some of that in a lot of detail, exploring Gödel, who was a logician, and then Bach, who was a notable musician of his day. And so I think that those structural similarities are very strong. There are a lot of echoes of mathematical things in music. But I think if we were to be a bit broader in our view, actually there are mathematical undertones in everything we do if we just know the sort of things to look for and look hard enough. It's just, I think music is an obvious one because there have been some real strong mathematicians through time who have also been very strong musicians.
Polymaths, yeah.
Mm-hmm.
So one thing that frustrates me, because working in science, having a science background, and just, understanding that the world is built on math, essentially, at some level or another. I get a little frustrated when I hear someone say, I'm never going to use this again. And I know you've probably heard this yourself. So when it comes to that basic math that people, for whatever, I kind of feel like there's a bit of there's a boundary that someone at some point has put up in front of students that says, you're not going to need this beyond now, or maybe this is too hard for you, or some sort of limitation, which I think is such a shame because we do use math every day in every way, and not just in baking pies. So what would you say if someone just said to you, I'm never going to use this again? Like, what would your response to that person be?
I would try and first suppress a deep sigh. But I think that what I would say is, let's take anything that we study at school. Let's take history. So you study, I don't know, the Napoleonic period. Where am I going to use that in my daily life? We don't necessarily use these things explicitly in our daily lives. But one of the things math does is it gives us a way of structuring how we think about questions, how we go about solving questions, how we take a big question, try and break it into little questions, solve the little questions, and then put them together to get a solution to the big question. And I think it's not going to be that you are going to have to derive this formula and then generate a table of values to use in your day job. And to be honest, I would not want you to do that, because if it's important enough for there to be a table of values, I would much rather it be done by professionals and looked over a bunch and error checked and made sure that it's right, rather than having someone do it each time.
Right.
But if you know, for instance, the mathematical underpinnings of how they're doing that, one of the things you could do is interpolate, you can interpret, you can, as will happen on exceptionally rare occasions, look at something and say, that just doesn't look right. And then don't take the next step until you've had an opportunity to talk to someone else and check it, think about it a bit, just in case there does happen to be a mistake in something. So for me, the power of doing a math degree is not necessarily, I now know how to do proofs in Euclidean geometry, and therefore I will become rich from that. But what it does do is it says, if I want to construct an argument, this is how I get from the beginning to the end in one particular way that's a sound, logical way. So I can at least then construct the spines of arguments, and I can then, fancy them up however much I want, but I've got a logically sound argument that I can make. And that, I think, is really an important thing. I think that being able to look at something and do a quick estimation is a really important thing. But in order to estimate something, you have to have some understanding of what's actually going on in that setting.
What's the frame?
So I think there's
there's
a lot of stuff where we can take this, not necessarily the specific facts, but the techniques and the processes, and develop an understanding that allows us to just be more comfortable making our way through the world.
Right. Makes sense to me. So I think that's a really good answer and a good approach. And I'm gonna bookmark that in my brain. So thank you. Now I'm going to do a deep dive in the other direction and talk about the things that you do. And I would like you to define for us, first of all, what is low dimensional geometry?
Mhm. So when the mathematicians that I hang out with talk about low dimensional things, typically we're talking about dimensions 2 and 3.
Okay.
And okay, and then the next question becomes is, well, Jim, what do you mean by dimension? So for the sorts of things that I work in, let's take surface. What I mean is a thing that I can build from little patches that look like pieces of the plane. So we have the nice Euclidean plane, and I have little patches that I can cut out of it. And I want to then glue them together and get something which, if I'm standing on it and looking only at what's going on near my feet, what I see looks sort of kind of like a piece of the plane. So I don't have weird things going on. So I don't have things that look like Y's kicking up anywhere. It all just looks like a piece of like a flat, maybe a hilly landscape, but nothing too weird going on. 3 dimensions, we have objects where near each point, we have a little thing that looks like a little ball in 3-dimensional space, so the inside of a globe. And then there's a subtlety, which is, okay, how do we then glue those things together? And that's when life starts getting very technical, because there are different ways we can glue things together, some of which will give us the same basic object in the end, and sometimes we'll get slightly different things going on. But mainly, at the moment, I'm mainly looking at 2-dimensional things. And I'm looking at 2-dimensional things that have a particular structure to them, which is, in essence, at each point, it looks like a Pringle. So at each point, I have a direction where I'm bending this way.
Okay.
And another direction where I'm bending this way. And so what I get is a little Pringle at every point. So at every point on my surface, it looks like a Pringle. This is a geometry known as hyperbolic geometry, or Lobachevskian geometry, if you know the Tom Lehrer song. And it's the geometry that I tend to work in. It's the geometry that's sort of, in some sense, most common among 2- and 3-dimensional objects, in some sense. And what I'm trying to do is, I have a set of questions about life on a 2-dimensional surface, and some of them are with collaborators like the guy who's visiting me now. Some are solo projects, and I'm just trying to work through and understand what's going on these objects that I don't have a good way of drawing. Because one of the things we know about them is we cannot accurately draw them in space, our normal 3-dimensional space. I cannot fit even the hyperbolic plane, where I ignore sort of all the interesting topology and I'm just looking at a flat plane with this hyperbolic geometry. It's impossible to faithfully stick that into 3-dimensional space. This is actually a result that goes back more than 100 years. I could stick it in 4-dimensional space, but that doesn't help me, because I can't really imagine things in 4-dimensional space in the way that I can in 3-dimensional space. And so one of the things we have to do is develop arguments and tools that allow us to handle objects where we can't actually draw an accurate picture of them. Okay. And that's another one of these sort of stepping points that we have during an undergraduate math degree, which, going back to a conversation we had earlier, which is, it's less dealing with things that we can draw and more dealing with things where we have a set of rules for how they behave, and we have to work within that set of rules because we can't actually draw them.
Okay.
I don't know if that's enough of an answer.
It's a very interesting answer, and it sort of pops up other questions in my head, but I also want to know, translating this for, let's say, quote, a real world practical application, what would you use this for?
So what would I use it for?
What would anybody use it for? This, but for you, let's just say.
So there is, over the last few years, there's been a bunch of work done, actually primarily by engineers, interestingly, that I'm gearing up to start diving into the literature on, which is, if we take a large network, let's say the internet, and when I say network, what I mean is I have a bunch of nodes, a bunch of dots, and I have them connected. Some are connected and others aren't connected, and I have this big thing that looks like some sort of horrifically large spider web where I have connections between some of the pairs of points. one of the things we want to do is to understand the behavior of these large networks. So for instance, a question that might reasonably come up is, if I think of a power grid as a large network, or even the internet as a large network, and I start to have a failure at some point.
Oh yeah, that's going to be
then
relevant.
I isolate that failure so it doesn't propagate through the whole network as a question. So we need to then develop an understanding of networks. And what people have been doing a lot of work on recently, just in terms of hyperbolic geometry, is that it seems that there are aspects of the behavior of large networks which make them look like they're hyperbolic in some sense. So that hyperbolic geometry can then start giving us a handle on the geometry of these large networks and how they behave. And so and this is what I want to do. I want to work through the understanding that other people have developed of the hyperbolic geometry, and then tie it together with what I know about hyperbolic geometry, and see if there's something interesting there that I can say that other people might not have said because they haven't come from the same perspective that I have. Now, maybe yes, maybe no. I think the chances are slim, but they're not zero, and it would be interesting to learn all this stuff anyway.
Fascinating.
And so one practical application is that. If we want to think more generally about the fact that space can be bent, and what are the consequences of, why do we want to study bent space, then all we have to do is look at some of the pictures coming out of places like Hubble and the JWST.
I was going to go there.
Because we're talking about things bending space and understanding the geometry of what's going on. I mean, that's really what Einstein did in his theories of particularly general relativity, is said, we need to understand how things bend.
Right.
And what he's doing, sort of the big fancy version of the geometry of spaces, whereas sort of hyperbolic geometry that I work in is a very special case sitting within that much larger geometric framework.
That's fascinating. So getting back to space then, so I know we're all agog yesterday seeing wonderful images from the new telescope. So looking at that from a mathematics position, like where did your brain go, other than setting aside the wonder and awe of the beauty of it? Like, where did your brain go in terms of math instantly?
To be honest, my thought initially went to what were the calculations? What was the math they had to use to actually design the thing?
Yes, I thought the same.
Because that's an incredible thing that they've done.
Yep.
And then another question I'd asked myself is, I know that, for instance, there are people who are studying origami with an application to how you can fold and then unfold things in space. And what I don't know is whether any origami type constructions came up in the deployment of the telescope.
You would think that it would, right?
I mean, it's origami is amazing stuff. And I think over the last few decades, mathematicians have realized how rich the theory of origami really is. Yeah. To the point where, so at the annual general meeting, there's a big annual meeting of the American Math Society, which is many thousands of mathematicians getting together to talk about math. And it's really awesome. Not everyone's cup of tea, but I think it's really awesome. And a few years ago, they actually were having several special sessions on just the math of origami and talking about folding and unfolding and what are the things you could do, and the sheer niftiness, the mathematical niftiness of paper folding.
Yes.
And there's literally math everywhere.
Right. I mean, you see the angles first thing, obviously, but then knowing that you're taking something that is a flat piece and you're making a structure, not just like, it's not something you crumble up. You have to keep angling, keep folding, keep doing it in just the right way so that it is a new structure. And then with that, you have a highly efficient use of surface area. So for something like a telescope with solar cells, and you want to tuck the solar cells in quite efficiently, because you have to save everything. You have to think in terms of saving of rocket fuel, in terms of how is it going to unfold. There's all these different dynamics at play to store a solar cell so that it can deploy the right way. And so before it ever gets off the ground, you've got to figure out the math of all that. So it's really fascinating to me.
And it's a beautiful dance between math and things like material science, because the math might say, this is a theoretically possible thing. And then the material scientists go, you expect us to build that? It's like, well, yes, we do.
And
please.
They need math. Material scientists need math because you're working with surface area situations. So what materials are going to give you, that efficient use of space, something that's really thin, but has the right material to be durable and perform whatever other tasks it needs to do. So there's math everywhere. There's literally math everywhere in space and on Earth in front of us. We're using math right now just to talk, which we couldn't have done years ago. So I feel that, what do you think, what are your hopes from this, from a math perspective, when we're just exploring the universe and we're making these discoveries? Everybody was instantly seeing, and this is also a physics situation, obviously, seeing the diffraction, seeing the curvature, the bend of the galaxies and some of the fields of view there, and all of that going together. Like the math there's got to be some really fun math to tease out of all that.
There is, and I think it's math that actually at this point is fairly well understood. I think if we want to think about where the next interesting frontier might be in terms of where math and physics meet, I think actually it's what comes after the standard model. Because I think one of particle physics, I think one of the things, there was a big article in the most recent Economist on it that I read, which is that we have the standard model. It's a very mathematical model because you're talking about symmetry groups and all sorts of exciting things. And we know that it doesn't, we know that we knew it wasn't quite complete, but we seem to be getting some experiments that are saying it's not quite right as it's written. And so there are a lot of people who are out there thinking about math and physics and the connections between the two of them, who are trying to see, does the math give us a route in to making sense of these experimental observations that are coming through now that we have the revamped LHC and the generation of colliders before? We have all this data that we're amassing. So there's the math of processing the data, and the math of processing data, huge amounts of data is again, just a general big frontier. But what then can we start to say about what's going on in these experiments where they don't quite seem to be agreeing with the framework we currently have? Now, this is not something I know really anything about, but it's fascinating to watch from the sidelines as, these discussions are happening. And as we get these things where it's like, well, these two numbers from the observation should be equal, and yet they're not. And so what's going on? And I think one of the things that a lot of the physicists are doing is, and have been doing for a long time, and I'm not sure they would like me to phrase it this way, but they're turning to the math to help them try and make sense of some of these things and to say, what might we be able to say?
Right.
And it's just all really nifty. And then you get things like brain theory, brain, B-R-A-N-E, the brain from membrane. So it's again, one of these extensions of, in mathematical physics, of what might be the theory of everything. You get string theory, you get all these sorts of things where people are trying to make sense of the world by using math. And sort of the miracle that keeps happening is when we take reality and we distill it down and we get some math out of it, and then we apply the math. We just follow the math for a while and then go back into the universe. We seem to find ourselves in a place where things still make sense. And that, I think, is just one of the most extraordinary things. Even where sometimes the math has taken off us in a direction where we weren't expecting to find our feet back on familiar ground, we still do.
That's such a beautiful thing. And it kind of underlines that common phrase of math being the universal language. It seems still to hold true. And it will be interesting to see how future discoveries in space test that statement. But it seems true. And that's one of the things I loved about Contact, for example, was like there was the prime numbers, the universal language, that a potential extraterrestrial civilization could communicate with others out there through math, which I think makes perfect sense. It's the most baseline thing that you could do. So what's your take on that? Does that make sense to you? Or
I think it does. I mean, I always go back to, and this might say something about me that perhaps I shouldn't say this publicly, but is an old movie called The Forbin Project.
The what project?
The Forbin Project, which
Forbin.
is a movie made out of a novel by a guy named, I think it's D.F. Jones, called Colossus, where we, the West, build a machine, a computer that will take all data and decide whether there's a threat or not. And then we tie all the missile commands into it in such a way that we can't undo it. And then we turn it on. And then it turns out the Soviets have one. And what happens is the two of them start talking to each other.
Yeah, like chatbots.
Through mathematics.
Yeah.
And start developing whole new branches of math before they decide that they have to take over the world for the good of humanity. So it's, that's where my brain goes. But I do think that there are some things in math, like prime numbers, where if anything is going to be universal, they're a good guess, because integers make sense, because whole numbers, because that's how we count.
Right.
I assume everyone will count things. And then the basic question of, can you break it into two pieces or not, where those pieces are, again, the whole numbers. And once you have that, you're off and running.
Excellent. Cool. So here's a kind of an off the wall question. What's the most outrageous thing that you think math applies to, like something silly, ridiculous, like popular in the current culture or whatever, and you could look at that and be like, math got you there,
Math got you there.
I mean, other than that,
I sometimes, and I know people have done this because I've seen projects on it. But you could talk about the math of Sudoku. So here's a question.
Yeah. Oh, for sure.
How many different ones are there? How many? So if you take away things like, okay, if I have a Sudoku and I just rearrange the numbers, I'm going to get another Sudoku. Yeah. Because if I replace 1 with a 2 and a 3 with a 5, etc., all the basic things should still hold true. But if you take away sort of those obvious things you can do, how many different ones are there? And I mean, algorithms for solving them, people have algorithms for solving them. You could ask, how little data do you need to figure out, at what point do you have enough information to say, at this point it's forced, the solution? There's only one solution. Questions like that, I think, are questions that a mathematician would appreciate for pretty much anything. You take any puzzle, any game, you look at the game of Go, which we cannot really approach mathematically at all, and yet we can still teach a machine to beat us at it. Not necessarily a wise idea to teach computers to outthink us and to have robot dogs running around and all sorts of things, but that's a different conversation to have.
Subject, like AI being one too, but yeah.
But I mean, there are all sorts of things. It's, we can use math to see inside of things. Right. So one of my favorite little examples, this isn't a silly thing, but suppose I have a blob, a rock, and I want to look inside the rock, but I don't want to break the rock. So there's a thing you can do, which is you start shining beams through the rock, right, and you measure the strength when it goes in and the strength when it comes out. So you know sort of the sum of the density along that whole line inside. And then you ask the question, well, if I know sort of how much of the beam I'm losing for each of the beams I put through the thing, can I reconstruct what's inside? And the answer is yes. And that's why we have CAT scans.
Yeah.
So, I mean, I don't think there's anything where you can't come up with a mathematical approach to looking at it. I think the Sudoku one is a slightly sillier one than the CAT scan, because the CAT scan, I mean, they did win the Nobel Prize for building a CAT scan, and it's, there's all sorts of remarkable things that are making life better for people coming out of that. But I think you can take anything and ask a mathematical question inside of it.
Excellent. And kind of related to, let's go to Sudoku for a minute and think about games. And, for people who might kind of have like almost a fear of math, or at least feel like maybe they can't do as well, do you think that games are a good way to help get over that and like participate more with math and become empowered in math?
I think that games are a great way of getting across some mathematical concepts, particularly, I mean, depending on the game you play, probability in a game of poker, that sort of thing, or even much simpler card games. But I think, again, it's a good way of thinking about a game and how to play a game, because keep in mind the theory of probability developed because people were playing games with dice. But you can imagine if there's no structure and you're playing a game of dice, you could ask the question, does 7 come up more often than a 2? I mean, it seems to, but how much more often, and these sorts of things. And it's only when you start digging into it that you realize how rich a field it is, and how easy it would be to take money from someone who didn't have the same mathematical understanding of the game that you did, which is, I think, may have been what happened historically when people started looking at the theory of games, because some of those early mathematicians not entirely reputable because they were coming out of that sort of, shall we say, more applied, more practical, I need to know things to help me solve this particular question, understand this particular thing.
Excellent. Well, I have asked a lot of questions, and I wanted to know if there are any questions that you would like for me to ask you, or that you would like for people to know about a mathematician, being a professor in math, any of the mathematics.
Don't be afraid of math. There are more and more resources that are coming out, things on Twitter, and I suspect Instagram and YouTube, which can help you work through interesting mathematical things at all sorts of different paces and timescales. It always makes me sad that math is the only subject that has sort of a disorder named after it, math anxiety. I think that's, it's become sort of a self-perpetuating thing that I would like to hope that we as people could, as humans, could break as a cycle. And so what I would just say is give us a chance.
Yeah, great.
Just give us a chance.
Wonderful. Well, this has been a fantastic chat, and I've learned a lot, and I hope that my readers and viewers and everyone who is listening in has learned a lot as well, because I feel inspired now to look at things differently and to look at Pringles especially quite differently.
Pringles are great, and not just for eating.
Yeah, there's lots of interesting geometrical shapes when it comes to snacks that you don't think about.
There's interesting math everywhere.
There is,
just
everywhere you look. So. Well, Professor Jim Anderson, thank you so much for joining us today.
My pleasure.
I've really enjoyed it. And thank you so much, Jim.
My pleasure. Thanks for having me.
Thank you.